All right, so we've solved the time-independent Schrodinger equation for the infinite square well, and so now we'd like to go through and look at some of the applications we can do. And just to note that we're going to be able to do this for many of our different situations, our different potentials, but we're just going to start doing it with infinite square well since we know this, and it's a fairly simple one to start out with. So again, the general quantum mechanics problem, you'll be given your potential. So here the potential is the infinite square well from section 2.1. And some initial wave function. So the first step is to solve the time-independent Schrodinger equation, find our energy eigenfunctions, psi n of x, and the eigenvalues En associated with that potential. So we've already done this. We did this last time. We're still sort of learning about that, but we're done with that. So now we're going to do the next steps. So the first thing is to write this initial wave function in terms of these energy eigenfunctions. So today we're going to figure out the trick that allows us to do that. So we're going to be able to express this initial wave function, any initial wave function, in terms of these energy eigenfunctions. So we're going to actually solve for this Cn. That's going to be our big thing today. Once you have that, then very similar, the same sort of idea as our time evolution rule, we're going to multiply each term by its e to the negative I energy time divided by h bar. And then what we have is we have the time evolved wave function. All right, so now we know what's going to happen as time goes on to our wave function. And usually these problems will have some extra step to calculate various things. Okay. So let's look now at what's called Fourier's trick. So what we're doing here is going to be very similar to a Fourier series. So you may have seen this, you may have not, but either way we're going to learn about it now, and this will help when you do sort of come across this stuff in math class. All right, so we're going to again assume that I can write my wave function as a linear combination of these energy eigenfunctions. And so then what I'm going to do is I'm going to take that equation I just had and I'm going to integrate on both sides. So first thing is I multiply each side by psi star m, okay, one of my energy eigenfunctions. So this guy is one of my energy eigenfunctions. And then what I do is I integrate both sides. So this is infinite square well, so I integrate from 0 to a on both sides. And so here I'm integrating times whatever my initial wave function is. And over here I'm doing it times this sum of the wave functions. And what I'm going to use is this fact that these wave functions are orthogonal. Okay, so here what I do is I can pull out the sum. So I pull the sum out, and I also pull out this Cn, it's just a constant. And what I'm left with is this thing here, which is what we use as our definition of whether something, a function, is orthogonal or not, All right, and so what this happens to work out to be then is this special thing equal to, right here, remember it equals to the Kronecker delta. And so it basically equals 1 when these two are the same, or 0 everywhere else. And so basically this side of the equation, this just turns into 1, and we can solve for one particular Cn. So our equation comes out to be right here. And so this is our equation. And so if I want to find the mth term in this sum, all right, what I do is I take the integral of the mth energy eigenstate with my initial wave function. Now that last part I think is pretty tricky, especially if you haven't seen it before. So I just want to go over it, and I think it can be helpful. So we do a lot of things in the book, and maybe we'll do it in class, where we're trying to do things in general, like we did that calculation for some sort of psi m. Well, if you get confused, try doing it for like a psi 2 or something. Okay, so here's psi 2. And so let's do this for psi 2. So on this side, we got this integral psi 2 star, my wave function integrated over dx. And that's going to equal this big sum. Now this big sum can be difficult to interpret, so when I'm kind of confused, I literally just start writing out the sum. And so this is psi 2, so let's write out the first term. So the first term will be C1, 0 to a, and we're going to have our psi 2 star. I'll forget about the function of x, as we know it's a function of x, and then psi 1 dx. So that's my first term. My second term then will be C2, 0 to a, psi 2 star, psi 2 dx, and then there's a dot, dot, dot. And now let's look at these integrals here. So this integral, we know that these two energy eigenfunctions are orthogonal, which means that this integral equals 0. So this whole term is going to go away to 0 here. Okay, this whole term equals 0. Now here, this integral, on the other hand, equals 1. Okay, so if I was to add up these terms, it'd be 0 plus, so that's 1 times c2. And the thing is you can write these out, but all the other integrals we have are going to be orthogonal, because this is the one that's c2. The next one will be c3, c4. Those are all orthogonal to psi 2. And so you're basically going to add a whole bunch of zeros here, dot, dot, dot. And so this sum turns out to be c2. And so what we mean is that c2 is going to equal this integral right here. And that's, of course, what we get. You know, if we take that last equation and for the m plug in a 2, you get this. Now let's try to interpret this a little bit and again try to tie it in to stuff we've done before. So we worked with the state vector before, and here's our state vector. So I can write my state vector as some linear combination of any of the two spin states, you know, positive or negative z, for instance. And we know, or at least we talked about, how we can write the CA and CB as inner products. Okay, of A inner product with the psi function. Well, this is, I would say, directly analogous to this. Okay, so the same thing, is just that now I can write any of my wave functions, and so we'll talk about the wave function at time 0, as a linear combination of my energy eigenfunctions. Now the big difference here is that this is a function and not a vector, and also that there's an infinitely many numbers of these, but the concept is the same concept. And this thing here, again, can be interpreted as the projection. Okay, so this long integral thing we just talked about, the Fourier's trick, is the projection of psi 0 of x onto the mth energy eigenstate. Okay, again, when we sort of mentioned this, but this is the same thing when we actually use the Dirac notation here. We'll call this the inner product, right? Because we know that when this integral equals 0, that means the things are orthogonal. And so what this is really telling us is it's telling us, you know, how much of this function is how similar is our wave function to the mth energy eigenfunction. All right, and we can do this for all of the different eigenfunctions and basically get this Cm from that. Okay, and then to further talk about the analogies here, we can go back and talk about the outcome probability rule from our rules of quantum mechanics. And so if we take some inner products, so here the inner product of positive z with psi, take the absolute square, that gives us the probability that our electron that was originally in the state psi would be measured to have spin positive z. And so now with this Fourier's trick, we get this Cn, which is Cn is a quantum amplitude. If I take the square of that, all right, what that gives us is the probability that a measurement of the energy of an electron in our original wave function will yield the value En, okay, which is equivalent to saying that it's in, you know, it's the probability that if we were to measure the energy of this wave function, okay, it would collapse into the psi n eigenfunction. And again, we can use this Dirac notation so that it even, you know, the analogy is sort of even stronger to us. Let's try an example of one of these problems. So this is from the book. So they give us our initial wave function. And so here it's a function looking like this here. And our goal, as will often be our goal, is to find the wave function as a function of time. And so here's a plot of what this initial wave function looks like. So how do we do this? Well, the first step is to find this Cn integral. So here is the Cn integral. Again, this is sort of our inner product of our wave functions, our energy eigenfunctions, and the initial wave function. And so for us, our wave functions are, again, the wave functions for the infinite square well. So here, and the book does this, which is trickier, as a total function of n here. So instead of doing this individually, it does it as a function of n. And then after the book normalizes this wave function that I gave us, the integral looks like this. And so you can look at the book and see how they go through and do this. We'll do a similar example in class to give us some more practice. But what can be often is it works out like this. And so the Cn's, again, this equation is for Cn is 0 if n is even. And then we get this kind of complicated formula here if n is odd. All right, so it looks like this right here. Now, basically, we're done as far as finding the wave function as a function of time. However, we want to sort of talk about it a little bit, but let's just sort of do that. So what this means is I can express my initial wave function this way, okay, as a sum where n is odd, okay, of the cn's times the psi n's. All right, and so for us, in our particular case here, that would be, there'd be a whole bunch of constants. So our Cn was like the 8 radical 15 over pi cubed, and then the constant from the wave function is 2 over a. And then again, it's a sum over n odd, where it'd be 1 over n cubed, and then our function looks like this here. And so this is a sum, and if we actually calculate this sum, it works out to be exactly the same thing as our initial wave function. So we'll show this to you in a second how you can actually do that. All right, and then here, just these are sort of the constants. Some came from the Cn, this bit came from here, and so now, you know, simply going back to our rules of quantum mechanics, to express this as a function of time, we just write it out kind of like this. Again, all these constants. It is this sum over n odd, 1 over n cubed, and then we just add in our time element. And so it would be e to the negative I ent over h bar. And of course, we remember that our en in this case was n squared pi squared h bar squared over 2 a squared. So this is actually the solution. Now let's spend a little bit of time talking about this and make sure that it makes sense to us. Okay, so let's look at this. So here again is our plot. Now the one thing that we notice is that if we, you know, draw a line through just about, you know, imagine this is the point A divided by 2. Okay, this initial wave function we had was symmetric about the center of the well. And so when we're doing these integrals here, all right, so for instance, okay, so we have our psi 1, which is just, you know, 2 over a sine pi x over a. All right, and then our psi 2, which is, you know, very similar. The only difference is now we have 2 pi x over a. So what does our psi 2 look like? Our psi 2, if I draw it, you know, just sort of real quick, this is our psi 2. Right, so what happens is our psi 2 is odd about the well. Okay, so this one is odd about the well, whereas this function is even. And we know from our calculating this that basically all those psi evens, so psi 4, psi 6, etc., are all going to be odd about the well. So this integral, all right, so I'm doing the integral in this case, okay, so for c whenever it's even, all right, I'm going to be doing this for an odd function times an even function. And so, of course, the answer should have come out to 0, which is what Griffiths calculated. But the thing is if you sort of think about that beforehand, you can kind of convince yourself that that has to be true. The other thing to note here is that this function, this initial wave function, is very, very similar, okay, to psi 1. All right, and so you can imagine when you calculate C1, all right, that it's going to be a very high number because they're very, very close to each other. The closer they're going to be, it's going to be closer to 1, right? If the function was the same, that C1 would be 1. And when I calculated C1, I got something kind of like this, 0.99927. All right, so it was like super close to 1. So this function, it's not exactly a sine function, but it's very close. And then furthermore, if you just calculate the first couple of these, so like C3 and C5, right? So for C3, I got about 0.036, and for C5, I got 0.0079. And so again, the way that this works is if I take that Cn squared, that gives me the probability of measuring this particular particle with the nth energy, you know, with energy En. And so you can see here that it's very likely that we're going to measure it with that first ground state energy level. And these ones, while it is probable, it's pretty small. And so just by looking at the picture initially, you can get a lot of information there from it. And then just to finish up our conversation of this, so here's an actual plot. Okay, so on here what I've plotted is the red is the actual plot of our initial wave function. Okay, so this is our actual initial wave function. And then the blue is our sum. And so here, this is just one term. So you can see, like we were talking about, these two functions are very similar. So this is kind of an unusual one in that the sum gets really close to our initial wave function very fast. That won't always happen. Okay, so here's two terms. It gets a little bit closer. And then here's 5 terms, and it's basically essentially the same function at that point. And so if you keep going, it gets more and more precise. All right, but that's sort of the idea. All right, and by terms in the sum, again, we're going through to this thing here. Okay, so I'm saying that our sum is a sum, so this is n odd of Cn times sine n. And so for us, the terms would be C1 psi 1 plus C3 psi 3 plus dot dot dot. And so this is actually keeping 5 terms in the sum, and already you can see that the two wave functions essentially are the same thing for us. So again, we'll talk more about this in class. And finally, I just want to talk about some important properties. So Griffiths talks about these, and I just wanted to sort of summarize. So here's some important properties dealing with these Cn. So the first one is that if I sum up the Cn squared, I should get 1. Okay, and so that's really important. That's basically that the system is normalized, right? Because we're saying that each Cn squared is the probability of measuring the system in the energy En, and so the total should be 1. And perhaps even more important here is this one here, that you can find the expectation value of the Hamiltonian, which again for us is the expectation value of energy, simply by summing the probability Cn squared times each energy. And so it gives you a sort of a weighted average of this energy. And this is not clear that this should happen, but a couple things come out of this. First of all, the expectation value of the energy is time independent. It doesn't depend on time. And this derives directly from the fact that the potential, if you remember when we started all this business in chapter 2, we assumed that the potential is time independent, okay, which basically means it's a conservative system. And so because that happens, we have the expectation value of the energy is time independent. And that's sort of our version of conservation of energy, right? Again, sort of an Ehrenfest thing. The expectation values oftentimes do what classically is done, and that's what's happening here. So the expectation value of our energy is time independent. Now what I'd like to do is just go through these proofs real quick in a more general sense. So here's the first one. So we just start with our general definition of normalization. And then what we do is we put in 2 sums. Now Griffiths does this too, but he does it without the time dependence. And so I think it's kind of nice to do it with the time dependence to show you that this actually does work. And so this is psi star, this is psi. And what I do is I make the 2 sums over different things. So this is over n, this is over m. All right. And then what we do is we start combining stuff. And the thing is because the Cn's and Cm's and the exponential pieces, because they're constant, okay, with respect to x, we can pull them outside. And the same thing with the sum. And so now we have this horrible double sum of all of this stuff here. However, the only stuff that depends on time is over here, and that seems really nice. That looks just like our orthogonality relationship. Okay. Also note that over here, this thing has to be the complex conjugate. The only thing that's affected is this negative sign here, and so you can see there's a positive sign over there. And so now what happens is we remember that this thing equals this funny little operator here, where again that operator is just equal to 1 when those two are equal, or 0 when they're not equal. And it just says that this basically, these, for our energy eigenfunctions, when we integrate over them, if it's the same one, that equals to 1, that means it's normalized. If they're different, it equals to 0, which means they're orthogonal. All right. And so what that does here is it basically, in this sum, means that m has to equal n. Okay. And so if we do that, then what happens is these exponential terms cancel, because it only is true when en and em are equal. And then when these two are equal, this is just the definition of Cn squared. And so we've got the sum of Cn squared equals to 1. And so I think when you first see these sort of proofs, it can be kind of tricky. Griffiths has some. One thing I think that can be helpful is when you're trying to go through these proofs. Okay, so Griffiths and what I did here is sort of a more formal for basically an infinite series. But what you can do is just sort of take two terms in your for your wave function. Okay, assume it has two terms and try to do the same thing. You can actually see, I think, easier where the cancellations come out. And then the same thing, he does basically a very similar thing. Again, he doesn't do it with the time, so I like to do that for you, where this is the expectation value of the Hamiltonian. So here's my Hamiltonian operator. And so again, I'm going to write out sort of the explicit versions of our two wave functions. And again, this is psi star, so it's going to make this one over here turn out to be positive eventually. The first thing I do is the H operator attacks over here. All right, and so what it's going to do is it's going to attack on this energy eigenfunction and come out as usual with an En. All right, and so then once that happens, it comes into almost a very similar, exact similar situation as last time. Everything here is just a bunch of constants. Now we have a new one, E sub n, and once again, this thing is going to equal our Kronecker delta, which is just 1 when these are equal, and 0 when they're not equal. And so if you set that up, it comes to be the same thing. So again, this is where the time-dependent part cancels. Okay, so this is sort of key. Because these are orthogonal, this will be En and En, and so this part will go away, and then basically we're left with a sum of these guys, which is going to be the Cn squareds times our energy. Okay, so this is important. Again, this is really a big thing. We're going to talk about it a lot in class. One thing to keep in mind is that if you're ever asked on one of these problems to calculate this thing, the expectation value of H, always do it this way. This way is almost always going to be faster way to do it. Okay, so we went through kind of the long way here to sort of prove this, but once we have this, you really want to use this. It can save you a lot of time.